Hello and welcome to the podcast today. Today I'm speaking to Scott Phillips. Scott has spent more than 30 years exploring how human beings inhabit digital worlds, importantly navigating today's questions of digital identity, ownership and accountability. He's the founder and CEO of Vaulted Ventures and a founding member of the Quantum Safe Alliance. Today we're discussing whether the internet can remain human when AI can forge almost anything, and quantum computing could challenge the security underneath it. Scott, welcome.
G'day, Errol. Thanks for having me on your podcast.
Yeah.
Yeah, where would you like to start with this?
Well, we have a lot to talk about. Yeah. And one phrase I want to avoid today is one that I've heard about the place quite a bit recently, and that's quantum Armageddon. So we're going to avoid that phrase, but we also want to talk about how we're avoiding that.
Yes, okay.
Let's start here, Scott. If a perfect AI copy was made of me or you, and indeed this is possible, like my voice can be forged in a matter of minutes, and then that voice was used to agree to something I never agreed to, how does the modern internet deal with that? And how do we fix that?
Well, that's a great question. And what you're essentially talking about there is identity. Like, how do you attribute a statement, a cultural position, political opinion, anything like that, to the actual person that made the statement and not attribute it to the person that didn't make the statement?
Right.
So this is I suppose, a subset of a broader question of identity, because you have the same sort of question around, well, what about if I, walk into a thing in a shopping centre, for example, and get my body scanned? Right? And this is something I know a little bit about, because I once upon a time created a turntable body scanner, and I would do this. I've got a gallery on, if you go to, for those playing at home, if you go to Sketchfab and look up The Robots Are Coming, which is the name of my holding company, then you'll find a gallery of 1,100 people in Melbourne that I have personally 3D body scanned. And so what you get there is this whole full body 3D mesh, and it really looks like them.
So
it's like
potentially that could be used
times a digital sculpture.
Like we talk about deep fakes. This is a reality.
Yeah, this is sampling. Right? So because that data is sampled from the person, it inherently is a question of identity. Now, and actually, I had a fun experience where I attended a brilliant event called SVVR 2014, the Silicon Valley Virtual Reality Conference and Expo in 2014. 2 weeks after the Facebook acquisition of Oculus, now Meta and Quest, right? And so that was a pretty exciting time, and I'd just at the last minute, as I was packing, I was, I might as well throw in the 3D sensor, this 3D camera that I use as part of my whole rig. I wasn't going to take the whole rig, but I thought I'll take the sensor. Everyone will have these out there though, so it won't really matter. Nobody had them. Nobody had it at all. And so I was able to use it as a gimmick on my little stall. And so people would come along and I'd be scanning somebody, and suddenly I had a queue of people wanting to get body scanned. And the deal was, you can come and get scanned, but you have to listen to me rave on for 2 minutes about my VR walk project, right? So, and so a couple of the guys that I scanned were buddies, and one of them, Jesse Georgery, was or is the founder and CTO of VR Chat. And so rigged him and his buddy up as fully rigged avatars off these scans. So that was pretty interesting, and you can easily imagine a world where this is just a service. It's like Pixie Photo in the mall.
Of course,
and you go in and get your full body scan, accurate body scan avatar.
Yeah,
that's full featured. Eyes moving, tongue, whatever. And then you can go and be you in the metaverse in cyberspace.
So here's the point. Like I could authorize that and use that however I wanted, because that's me and that's my IP, so to speak. But someone else might obtain that digital copy or that digital information and use that avatar of me to be me in some circumstance, represent as me, but it's not actually.
Hmm.
So
Yep.
how do we protect against that?
Well, that's the perfect segue into my number one concern these days, which is the vaulted objects infrastructure. All right. So the answer to that question really is that you shove that info, whether it's the 3D scan or it's some political opinion that I might have professed, whatever, and into the vaulted object. Now that vaulted object is cryptographically owned by me, by you, if it's you. So a vaulted object enables, for what we think is the first time ever, the possession of digital content. And I mean possession in the legal sense as much as the practical and digital sense.
Mm-hmm.
I call myself a legal technologist.
Okay.
So I have a law degree.
Yep.
But I've been building software.
And you're also an IP specialist as well, right?
Yeah, I specialise in intellectual property
Mm-hmm.
law to some extent, yes.
Yeah.
And so possession is really important at law, right? There's a phrase, possession is 9/10 of the law.
We hear this, yeah.
So, and possession is one way that you own things,
Hmm.
right? Now, you might not have all the receipts to everything within your house that goes in your car, whatever, but it doesn't really matter because you own them because you possess them.
Right.
You are taking actions to stop other people from just walking off with them, right? You have a lock on your door, you have a lock on your car. And by doing that, you own stuff, right? Unless somebody's got a superseding right to come in and, regain possession of their stuff, then you own it.
Yeah.
And so a vaulted object is a mechanism for doing this in the digital world.
Right.
As part of the internet protocol.
Mm-hmm.
Right. So the story of Vaulted Ventures, which is the business that's bringing this to market, is really the story of my relationship with our cryptographer.
Okay.
And so he has created this entire framework. We've been working together for some 8 years. I'm sort of the master's apprentice in this sense. And so yeah, this concept of a vaulted object and possession is really interesting for a legally trained technologist. In a purely digital sense, but it's, well, I mean, I say purely digital, but it's in an actual legal sense because it's through this element of possession. And pardon my French, but what the French would call a chose in possession. Shoes in possession. And a chose in possession and a chose in action are the two and the only two ways that you can legally own something. Own a thing. Chose means thing. It's a thing in possession. Or it's a thing in action. Now, if you have to bring an action in court to recover possession, like you own a house and you've leased it out and the tenant's not paying their rent or whatever, and you need to get the sheriff in and recover possession, well, that's a chose in action.
Mm-hmm. Okay.
But if it's something that you own because you possess it, it's a chose in possession. And similar with a vaulted object. Now, what we're doing is we're bringing this feature and a whole bunch of other features and functions to the internet protocol.
Okay.
Because the internet didn't really come fully formed. It's still early. It's still nascent.
Still working this out. Yeah.
And to your question about the identity aspect, it didn't come with an identity protocol.
Was not even considered. Yeah. And we've tried to latch on these pieces on the side that try to give someone an identity, like when you log into your bank account or when you log into your Google email. Correct. We've tried to add these pieces on that identify you, but those pieces can be easily forged by someone else and are regularly.
Yeah, absolutely.
Yeah. So we've relied on this technology of encryption through recent times, and I'm talking the last, decade, 2 decades, this subject of encryption. And encryption is something that, and I'm going to oversimplify here, Scott, because you know this better than I do, but encryption is the subject of how to obfuscate data so that it can only be read by a person who holds a key to that. And this has done reasonably well over time, but I understand this is not something which will continue to hold in the future.
Absolutely. Absolutely. So we are staring down both barrels of the dual revolution within the IT revolution at the moment, right? One, of course, is AI, and many people are aware of this now. And the other is quantum, and that's growing in awareness presently. It's well into the S-curve. And so there's a bit of a... I'll just set this up, right? So there's an old thing called a Caesar cipher. It's one of the earliest types of encryption.
Uh-huh.
And a Caesar cipher, you essentially, there's a few simple versions. Imagine rolling a piece of paper around a pencil. This is not a Caesar cipher, but roll a piece of paper around a pencil in a spiral, sticky tape it at one end, roll around, and then write a message on it, write a couple of lines as you turn it around.
Okay.
Right? Now unroll it, and you just scramble the thing. You can give that to somebody, and they won't have a clue what it is.
Right.
Unless they have the right size pencil.
Right. Okay.
Mm-hmm. And Caesar cipher is just a letter substitution cipher. So you say ERROL, but we're going to add 5 letters of the alphabet, alphabetically, to that. So E becomes whatever the 10th letter of the alphabet is, etc. And now it's also confounding. It's not unbreakable, though. If you know the algorithm, you know...
Right.
Yeah.
Yeah, even if you don't know exactly that it's 10, for example. Like you can work it out. Like you can look at that and go, okay. And then if we were to feed that into an AI model, probably milliseconds.
Yeah, totally. We'll smash it in no time. So then, cue discussion of August Kirchhoff's.
Mm-hmm.
Now, Kirchhoff's wrote on this topic, and he basically said, look, your cipher should, if it's any good, you should be able to tell your adversaries exactly what you're doing, not give them the key, and it'd be totally fine.
Right, yeah.
So his idea is that the key is primary. So, and otherwise you're talking about security via obscurity, right? And that's what these early ciphers were trying to do, right? And then you've got things like the Enigma machine, which was a fancy typewriter full of rotors, and so rotary encoding.
Used in the Second World War.
Yeah. And so, and the story of Bletchley Park, and a big part of the Allied victory in World War II, was that at Bletchley Park, what they worked out is that all of these telegrams to U-boats ended in the same way. Or they started with a date, and they ended with the same 2 letters at the end.
Okay.
H.
Uh-huh.
Do you know what that stands for?
No. Yes.
Heil Hitler. All right. Dangerous thing to say on a podcast.
Yeah. I stopped myself, but...
Yeah, don't take me out of context. So that, the HH at the end was a big part of the reason why the Germans lost the war.
Right, because they could go... Obviously,
we
know that's what it says at the end.
Yeah.
So you can work backwards from there.
That's right. Because it wasn't perfectly secure. Because if you knew something about it, you could then...
Sure, we know what all the H's are. We know what all the... Yeah.
So that's pretty hilarious.
Yeah.
Now, that principle comes into play because of the second part of this revolution I'm talking about, the quantum revolution. So these early ciphers were symmetric ciphers. They had one key.
Right. Yeah.
Right? So you had to have a way to transport the key securely. And, there's plenty of movies been made about, how to do this. And that's not really great when you're talking digital networks, internet, right? Because if I want to encrypt a message and send it to you, well, I can do that. I can send you the cipher. It's encrypted, right? But how do I get you the key?
Yeah.
Because you don't have that, I have that. I can't just email that to you.
No, because it can be stopped and obtained in the same way as the original message can.
Yes,
Yeah.
somebody's hacked a mail server and the man in the middle, and that's a problem.
Yeah.
And if you did have a way to send the key totally securely, you wouldn't bother. You would just send the message totally securely.
You send the message that way, yeah.
Yeah. So then Rivest, Samir and Alderman, otherwise known as RSA, came up with this idea of public and private keys that are mathematically related to each other. And sort of amazingly, because of mathematics, you can encrypt with the public key and decrypt with the private key. And that unlocked a whole thing, we call it cybersecurity, right?
Yeah.
Because the mathematics of this is simple in one sense, which is that the private key is actually two numbers, two really big numbers typically, that when you multiply them together equals the public key.
Aha.
So now if the public key, let's just make these numbers small so we can talk about it and get our heads around it. Let's say that the public key that I've made public on my website is the number 21, right? Now you have to work out what are the two largest prime numbers that when you multiply them together equals 21.
Right.
And anyone who's been to primary school and paid attention to their times table can probably remember 3 sevens 21. So you can do that in your head with a bit of education, but now make that 21 quadrillion and something.
Yeah.
And now try and do it.
Yeah.
Right?
Yeah.
That's a hard problem. NP hard problem, actually. And so because you have to basically trial and error. Right? There is no algorithm.
Right. You have to just try one, try the next, and so on until you work it out. Yeah.
In mathematics, you call that a trapdoor function. It's actually quite easily. You add two hugely large numbers into a calculator, bang.
Yeah.
You've got the product.
Yeah, but trying to figure out what those two are. And so this is why that style of encryption is good, but not perfect.
Yeah, that's exactly right, actually. And the guy that proved this is a guy named Peter Shaw. He created Shaw's algorithm, which, as far as we know, has not been able to be actually implemented yet because it's a quantum algorithm and it requires a sufficiently capable and fault-tolerant and cryptographically relevant, which is sort of all the same thing, quantum computer to implement.
Okay.
So, but essentially, what a quantum computer is, well, let's just talk about what a classical computer is for a start.
Yeah.
And I'm drawing a sort of very simplified analogy. So imagine you've got a desk in front of you with an oblong array of 20-cent pieces on it, right? Some are heads and some are tails.
Yep.
Let's call them zeros and ones, right? And you can flip them over anytime you like, change the zeros and ones. That's a classical computer, right? Yep. It runs on bits.
Right, and the calculations of those zeros and ones.
Yeah, that's right. Yeah, and a whole lot of other complexity.
Right, but at its simplest level, that's
correct.
What it's doing. Yeah.
And now imagine that you can somehow get them all and spin them, all of them at the same time, right? That's a quantum computer.
Right. Okay.
Right?
So they're neither a zero or a one. There's something in between.
Quantum bits.
Yep.
They have a probability of being a 0 or a 1.
Right. Okay.
Sorry, what were you saying?
Sorry, I just said they're not a 0 or a 1. They're somewhere in between.
Yes, that's right. Yeah. Absolutely. Yeah. And not only that, but they're talking to each other.
Yes.
Right? They're interacting in multiple dimensions of hyperspace, if the quantum physics is to be believed. And the good old joke is, if you think you understand quantum physics, you don't understand.
You definitely don't understand it. No, the best we can do is understand a model of it. We can understand an idea or a concept of it.
Yeah, that's right. And also, it can be tested empirically, and that's why this is actually becoming real. That's why the development of quantum, if it was just an idea that you could hold in your head and that was it, we wouldn't have anything like a quantum computer. Because it can be tested empirically, then, you know.
So these things are in development and there are workable models, but they're not stable yet. And so the work continues to make them stable, to make them a usable tool.
Yeah, they're not stable enough yet.
Right, stable enough. Okay.
You can get some like microseconds or milliseconds of stability if you're only talking 3 or 4 qubits. But 3 or 4 qubits is nowhere near enough to do these calculations, and not enough for Shor's algorithm, that's for sure. No pun intended. And so, but we are on the trajectory towards scalable, stable qubits.
Okay.
And if you're paying attention to the cadence of the news stories around this, whoa, this is happening. Boom, 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 boom. On the physical side, as well as on the mathematical side, there's advances in the mathematics to simplify the problems and require less and less fault-tolerant logical qubits. And so what that means is that the quantum timeline for the thing that we can't mention is coming closer.
So my understanding is this, Scott, and you can definitely correct me here, but the traditional encryption methods are working at the moment and maintaining some security of the internet. That is,
well, but we don't know.
Right, at this moment in time. So if I use a password to access my banking, I can reasonably assume, without some human doing something stupid, that data will remain secure. And people do stupid things and databases get breached, but it's not because the encryption fails, it's because a human fails. However, if quantum computing becomes a reality, or I should say when it becomes a reality, then that all goes away. That encryption is not good enough, and we need a new method of encryption.
Yes, because somebody implements Shor's algorithm on a fault-tolerant quantum computer, and they're able to prime factorize your public key,
right,
and work out, not in millions of years, which it takes with a classical computer, but in minutes or seconds,
right,
can calculate what those 2 large primes are, which is your private key, and is the private key mechanism for all of PKI,
right,
public key infrastructure.
Right.
Now, this is the stuff that, well, formally, the standardized version of PKI that's most used and most known is X509. Now, our cryptographer was part of a very small team of people in the 1980s in Geneva at the ITU that standardized X509.
Okay.
Right? So he's known where all the bodies are buried on this stuff for 35 years. And he's, taught me a thing or two. So that X509 protocol is what's behind the scenes in SSL, TLS, and puts the S into HTTP.
Yes.
It also puts the security behind digital signatures over at Adobe Sign, DocuSign, and the long tail. And it's also inherent to blockchain architecture.
Right.
It also protects your credit card. So it enables all of e-commerce.
Right. Yep.
Private messaging.
Right. And health information.
Oh yeah, government and corporate
Everything.
databases.
Yeah.
Absolutely. Yeah.
So here's the problem that I see, Scott. Like, anytime I put data into a website, it goes into a database, and if that information is somewhat private, it is encrypted in this way in that database. Like, the programmer has built that in, meaning that if I was to open up that database, I can't just read your personal information. I can't read your password. It's been encrypted. But here's the problem. I could steal that database today. It is encrypted today, but in a year's time or in 5 years' time, the technology will be available to decrypt that without having those keys.
Correct.
And so something stolen today could be at risk in 5 years.
Yeah, absolutely.
Harvest now, decrypt later, I believe it's called.
Yeah, harvest now, decrypt later, sometimes called store now, decrypt later.
Okay.
Otherwise known as a harvesting attack.
Right.
But yeah, so now when you, in the full analysis of this, there is only one class of data known to humanity that is not vulnerable to a harvesting attack, and that is information that is encrypted according to ITS, otherwise known as Information Theoretic Security.
Okay, explain that.
Right, so we're going to go back on a historical tour again. So slightly more modern than August Kirchhoff's is 1919 and Gilbert Vernon. So Gilbert Vernon published on the Vernum cipher, what is now known as the Vernum cipher. And a Vernum cipher is an exclusive OR, really, between the message and the key. And what's super cool about this is that if you imagine this is represented in binary, so it's a whole string of zeros and ones, but it's the message. This is the thing that can be converted to ASCII and read. And the key is the opposite of that. This is like chock-a-block full of entropy. It's just random
randomized,
stuff, right? Now, with the XOR, exclusive OR, you can essentially press those things together and you get a cipher that looks totally random.
Okay.
But what's cool about the exclusive OR is that you can take that key and press it into the cipher, boom, you get the message back.
Okay.
Right? Just by the way the 0 and 1 maths work, right? With an exclusive OR function. So he published on that. And then fast forward a few decades, there was a chap named Claude. Well, you would have heard of Claude the AI, no doubt.
Named after this individual.
Yeah, named after Claude Shannon, who was undisputed genius working at Bell Labs in the 1940s and 50s. And so Shannon published a paper in 1949 based on the Vernum cipher entitled Communication Theory of Secrecy Systems. And so remember the date. It wasn't that far away from Bletchley Park in World War II. So he dug into, and in fact is the undisputed godfather of information theory. Didn't exist prior to Shannon. Right. He certainly formalised the field. And so in this paper, what he did is he set some rules around the Vernum cipher, 3 simple dance steps to make a form of encryption that remains secure against unlimited computing power for an unlimited period of time, right? Proven by information theory. So, which he made up, certainly, and has stood the test of time for the last 77 years.
Right. Okay.
It's just taught in, first year computer science and, whatever, engineering. So essentially what he created in this paper, what he published in this paper is called the one-time pad.
Okay.
And it was called a pad because in 1949, you wrote the key down on a pad of paper.
Right. Okay.
And it was a one-time pad because that's one of the dance steps, you can only use it once.
Right. So as soon as you've decrypted something with it or encrypted something with it, you throw it away.
It's gone. Yeah, that's right. And so the 3 dance steps are, 1, the key is as long as the message. This is not how PKI generally works, right? We're talking like keys of varying lengths,
60
bit, 256 bit, whatever. The bits, the number of bits is the same as the length of the message.
Okay.
So that gives you very large keys. And the second step in the dance routine is that the key needs to be derived from a source of true randomness.
Right.
Right. Now, you see the wallpaper behind me? Not truly random.
No, definitely.
No, right? It's a repeating pattern. And it turns out that if you have a pseudo-random number generator, which you do, it's called a computer.
Yeah.
A computer can't generate true randomness via software.
Yeah. Yeah. That's right. This is a fact that shocks a lot of people.
Yeah, that's right. Because random number generators, well-known things, right?
What's the company that has the wall of lava lamps? I can't remember who that is now.
ICANN.
Is it? Yeah. Okay.
Yeah, ICANN, Cloudflare.
Cloudflare has that. Yeah. Yes.
I think ICANN was well and truly the first to do that.
Okay.
I don't get any credit. No. So if you were to generate wallpaper with a TRNG, a truly random number generator, you wouldn't see that pattern.
Of course.
Repeating.
Yeah.
But if you look at if you can visualize a pseudo-random number in graphical form, it looks a bit like wallpaper. You can actually see the pattern repeating.
Yeah. Yes. You just take that larger lens and you can see the pattern.
Yes.
Yeah.
So that's an attack vector.
Of course.
When you're talking unlimited computational power at the disposal of your adversaries, you don't want that.
Yeah.
Right. I didn't actually ever think that this wallpaper would come in handy, but it does. So, and the third dance step is it's a one-time pad. You can only use it once. So that third requirement creates a bit of a stumbling block for usability of this stuff. So, and however, this ITS encryption, the one-time pad, has been used routinely for the last 77 years by all the world's militaries that know what they're doing, the security agencies, diplomatic corps, governments and sovereigns and whatnot, right? To protect their top secret stuff.
Right. So it's complex, but that's the requirement.
It's operationally complex and cryptographically dead simple. It's an XOR.
Yeah. Yeah. So it's a simple
is,
calculation to come up with the encrypted message. Yeah.
Absolutely, yeah. But the OPSEC is a bit tricky, the operational security. So and something to say about this is that computers are really good at exclusive OR operations.
Right. Yeah.
Like it's one of the basic primitives.
Yeah.
On a transistor, essentially.
Yeah.
Right?
Yeah.
You can wire a few transistors together to make an exclusive OR function in a microsecond. Right? And so what that means is that this style of encryption, it's a no-brainer for modern data centers, for modern CPUs, GPUs.
Yeah.
Just rip through this stuff. And so where does that leave us? The OPSEC problem is that if you're a military HQ and you've got to securely talk to your submarine, then what do? You've got that whole can't email it problem. So you have to give it to James Bond to get in his Aston Martin and drive to the dock to meet the submarine commander, exchange the keys that you can only use once.
Yeah, right.
So, but you can, fit plenty of keys on a pad of paper, right? So, or on a hard drive, let's say. And so, but that's a royal pain. And essentially what our infrastructure is, as far as we know, is the world's first ITS KMS. It's an information theory security-based key management system.
Okay.
Right? So we have solved that key management problem.
Made it portable? Is that the...
made it work over the internet.
Okay.
So yeah, portable, but not portable
digitally
portable on the internet.
Yeah.
So, and that's the important thing, right? Because you want to be able to do this through an API anytime you like. You want your agent to be able to bang, 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 create vaulted objects. And
so you can use this vaulted object then to sign something to say, yes, that's me, and then that can't be forged. You can use it to encrypt a document so that can't be read by anyone other than a person who's intended.
Yes, absolutely.
Okay.
Right.
All right.
And stay secure against the cloud service provider underneath our infrastructure, or whichever cloud it's on, because these things are JSON files.
Right, so they can sit anywhere there is a server.
Yeah, heavily leveraging the JWT framework for those playing. And it's just a text file, and you can push it out into Google Cloud or AWS or bare metal or whatever.
So does this solve the problem of a future quantum computer? And how?
It does. Yeah.
How does it do that?
Well, because of Claude Shannon's proof, like he proved that OTP does, right? And that's why the militaries and the security agencies of the world have been using it exclusively for their top secret stuff ever since. And our proof is an extension of Shannon's proof. So we have a way to prove that our KMS extension to the one-time pad is also ITS in its security profile.
Okay.
Right? Because if it's not, then it's all nonsense, right?
Yeah.
And if you don't have a proof of the security model of the encryption that you're talking about, then, well, is it going to be secure against the future of quantum computing? Right? Because the future is a long time. And the future of quantum computing, I would suggest, is a...
Okay.
I mean, this is why I think I don't tend to use the term post-quantum cryptography, because I think it's confusing to people.
Yeah, sure.
It's like, what, is quantum over? Have we reached the end point of quantum?
Yeah.
No. We haven't even started quantum.
No, we're at the pre-stages, very much so.
Yeah.
But very much into it, because as we discussed, a piece of data that's stolen today that's encrypted is at risk in the future because it's not encrypted with the right technology today. It might be secure today, but it's like stealing a safe out of a bank and being able to grind the doors off of it tomorrow.
Yes, absolutely. Yeah. I mean, fast forward your brain to 20 years in the future when quantum's been around for a decade or more, most likely a lot longer, and see how your security architecture stands up then.
Right.
Because if you've got data that just cannot leak out, whether you're a bank or a national security agency, then you're going to have a problem, right? And it's going to be embarrassing and potentially, existential, catastrophic. So, but we won't use the A word. So that all becomes pretty interesting then. Really what we're talking about is the adversaries, whoever they are and wherever they are, because they're not always in an obvious nation state. Sure. They might more likely to be within your national boundary, right?
Could very well be, yeah.
Borders. So it's really not a geography. None of this is really a geography issue. And so what happens is that all the data, as you were saying, that I like the word exfiltrate. All the data that gets exfiltrated doesn't get decrypted straight away, but it gets taken and stored. Then the adversaries just have to hang around for long enough, and they know that the time is coming to then it be open sesame. All right. Now, this is where I get into trouble with some people, because what's really interesting about the PQC story, and PQC is being big time sold to enterprises, the NIST standardized PQC algorithms, essentially the state of the art in terms of hardening the security profile of PKI, this public and private key business, which we don't have public keys. It's completely symmetric encryption, and so they're trying to harden the public keys essentially. And so they also talk about this idea of crypto agility. And this is interesting because agility is generally a good thing, right? You want to be agile, and you want to be agile in your coding frameworks, and you don't generally want to integrate especially new and important stuff deep into your code base. You want to do it through an abstraction layer and sort of pop it up on top, if you like, so that you can, if you need to, swap it out later on. And this crypto agility story is being sold as a feature of PQC. And so a smart enterprise client would then have to ask the question, well, why do we need to swap it out? Because it's not going to work. It's going to break eventually. Okay. And they know it. And that's why they're talking about crypto agility and selling it as a feature.
Right.
Right.
Yeah. Okay.
But what happens to your data? Error.
Yeah. Well, and this is the very core of what we're discussing. Like, an individual's data is not secure right now, and we can't expect it to be. I think that's the problem. And we discussed this actually, Scott, but there's an additional layer to this problem, and that is the human element. Data breaches have occurred primarily because a human has done the wrong thing. And how do we protect against that?
Well, you can't legislate common sense. That's one of my favourite expressions.
Yeah.
So, and none of this is going to stop the $5 spanner attack, right?
No. The junior dev just leaving the unencrypted database. out in the open.
Yeah, well, the $5 spanner attack is somebody buys a spanner for $5 and comes into your room and holds it over your head until you give them the password.
Right.
So there's always a human
There's
element,
risk.
or human security, let's call it. Human side.
But that goes back to what you said at the very start, which is the point that ownership is dependent upon possession, and the $5 spanner attack involves stealing. So
correct, yeah, and there are laws against that.
Yeah, yeah. I mean, as much as any of this is important to someone who's doing the stealing.
Yeah. Well, there's also locks on doors.
Yeah,
right? So
yeah.
If you really don't want the $5 spanner attack, then leave your phone at home in a safe or whatever.
And what we're talking about here is just building better and better locks.
Yeah, digital locks.
Digital
in this
locks.
Case.
Yeah.
But physical locks don't go away, and they don't become unimportant. So, and then there's the legal locks, I suppose, as well. The criminal law.
Okay. Right.
Yeah, and the civil law.
You've talked about a subject called governed AI. Can you explain that? How does this relate?
Yeah, so there's many conversations around AI governance. And to me, AI governance sounds like the Leviathan of government coming and dictating how it's going to be.
Right.
That's it.
Right. But before you go on, there is a law in this, which is that you can't legislate against technology if you consider that technology to potentially be harmful. The reason you can't do that is because someone else is still going to create it. If it can be created, someone else is going to do it.
Yep, that's right. And so the analogy that I like to use is that governments have the legislative lever that they can pull. And oftentimes, it's the only thing they have.
Right.
Maybe they can lean on the central bank for interest rates or something sort of similar.
Right, run an education campaign on TV or something.
That's right.
That's
very $50 million on an ad.
Yeah.
And so they tend to reactively pull that legislative lever, but under the floor, under the hinge where that connects to the mechanism, there's nothing there.
Right.
Right. So if you've got, there are certain government departments in Australia that have come in for critique, let's say, about their ineffectiveness in terms of prosecutions and enforcing the regulations. Australia's not unique in this. This is happening all over the place. And imagine the world if the enforcement of all laws was automatic and complete all the time.
Right.
You at least have a possibility of a utopia, right?
This is unlikely.
Yes, it's highly unlikely because that is mostly that enforcement piece is observed in the absence, in the breach, right? So, in other words, governments need something underneath the floorboards to connect to when they pull the regulatory lever, the legislative lever, so that they can actually cause some enforcement to happen. And mostly there is nothing, right? Except for these, large government departments that sometimes prosecute some people some of the time.
Right. Yeah, but even so, it's very difficult. And I'm just gonna interject with an example of this right now, so the listeners probably understand how this is illustrated. So recently, our Prime Minister, and I'm talking in Australia here, has said that he wants to harden copyright law so that AI tools can't steal that data without recognizing the artist or the owner of that data. The problem with that is if that data exists anywhere else in the world, as it normally does with a digital piece of information, there is nothing that can be done to protect it against that. There is nothing that can be done against data that's already been stolen. And I'm talking about video, music, speech, illustration, art, already been stolen, long gone. The horse is bolted long ago. And so we can talk about all that all we like, but at the end of the day, it becomes a bit of a PR statement.
Yeah, because of the lack of that enforcement mechanism.
That's right. So the inability to enforce that, like it just becomes this is a nice to have, but not really possible.
Well, I have opinions about this,
Okay.
as you probably gather.
Yes.
So the AI industry has been in a race condition, absolutely, since people started paying attention to it. So, and the company that stopped to pick up the pieces of copyright licensing on the training data, if they did stop, they would have gotten steamrolled by all the other companies.
Absolutely. Yes.
And they would be forgotten about nobody's. And so they weren't actually able to stop and sort out that big mess.
Yeah.
With no technology framework to even attempt it. So they didn't.
All right. It was a beg for forgiveness rather than ask for permission.
100%. Yeah. Now, the fact that you have to beg for forgiveness doesn't mean that the laws that you've contravened disappear. Right? Unfortunately for the AI industry, I'm sure they will not. But what it means is that they have to come in from the cold eventually, or the rest of the world has to agree that copyright is no longer a thing, right? Which we haven't done. No, I don't think so. Although I've got opinions about that too. Because, well, yeah, let's just open this one. The US Copyright Office, did you hear their statement in relation to copyright on purely AI-generated content?
I believe it was that it can't be copyrighted. Is that correct?
Correct.
Yeah. Okay.
Right. Now, you could certainly suggest that the US Copyright Office just shot themselves in both feet and the head simultaneously, right? Or you can say, well, no, it's not human authorship and copyright, rests in human authorship.
Right. But also if I add 5% of my own skill and talent to that, then it becomes copyrightable.
Well, what's the value of a prompt?
Sure.
Right? The prompt is the expression of an idea in your head. You can get a patent on an idea.
Sure.
And you can get copyright and design registration and a few things on the expression of an idea. And this is the foundational tenet of intellectual property law, is the idea-expression dichotomy.
Okay.
Right? So, and that really helps to understand why people... So, but both of those things are important. And so you can then start to tease out the argument that, the USCO should recognise copyright on AI-generated content. And I think they probably should, and it would be better for them if they did. Maybe not better for the AI industry. Who knows? There might have been some pressure, some political jiggery-pokery going on in the background. Wouldn't be surprised. However, and despite the fact that I've, been a bannerman for copyright law at various times, at least in my own head, writing papers, etc., I don't care if copyright law dies in a ditch, right?
Okay.
Because there's another element to intellectual property law that most people studiously ignore and is very potent, is very powerful, and it's called the law of confidential information.
Okay.
Right? Otherwise known as trade secrets, and arguably way more powerful than any government monopoly patent or rights under the Copyright Act, etc. And this is the foundation of NDAs. Plenty of people sign non-disclosure agreements, right? Now, if you could have a cryptographic, secure, quantum-proof digital framework for content, even AI-generated content, and when you allow other people to access it, you also have a really quick and efficient way for them to agree to the terms of the non-disclosure agreement baked into the request.
Process itself, yeah.
Yeah. Then they effectively have to sign a non-disclosure agreement in order to look at your video, image, 3D world, whatever the media is, whatever the data is. And if you do that, it stays confidential information. And then the next person can do it on the same basis. With
the same agreement, yeah.
So it stays confidential even though people can access it, but they access it through agreeing that it stays confidential. Yeah.
Okay. All right, let's go back to the vaulted object then. So the vaulted object is the core principle. It can be confusing, but I want to simplify it. So I'm a user. I want to secure my data. I want to prove my identity on the internet. What do I do? How do I do this? I mean, I know this is not a tangible thing at this time we're talking about it, but what's the concept? What's the idea?
Well, it's tangible in the sense that the whole infrastructure has been built and deployed for purposes of regression testing, and we're in the process of getting our ducks in a row so that we can pull the trigger and make this available through API.
Okay.
So the answer to your question is really it's just an API call.
Right. Okay. So any user will be able to do it as simply as they use their Google auth to log into something. That's the idea.
Yeah, that's right. Yeah.
Yeah.
And we'll perhaps throw an image up on the video. You can edit it in.
Yeah.
But that describes a user with a device that binds to the infrastructure. So
yeah,
this is a surveillance device.
Yeah.
Right.
Okay.
Except there's one part of it that isn't, which is the TPM, the Trusted Platform Module.
Yeah.
And if that's integrated into the processor, it's called a Trusted Execution Environment. And that's where you can store a secret so that nobody else can get it.
Right.
In the hardware of your phone. It's probably the only secure thing about your phone. Really.
Right. And that's the part that's locked to your fingerprint or your face.
Yeah, that's right. Yeah.
Yeah.
And in the same way that Google Authenticator and similar apps do.
Mm-hmm.
And so our system is, well, I actually used to use that. And now we've hardened that, and it's the same design pattern, but it's cryptographically hardened. And that creates a binding. That's sort of like the control line into the vaulted objects infrastructure sitting in the cloud.
Yep.
And so inside of the infrastructure, and this is really, starting to unpack the Russian dolls of our security model. Inside the infrastructure, for each tenant, for each user, is a key generator.
Okay.
Right. So if somebody happened to get access to our infrastructure, they would find exactly 0 keys.
Right.
That's an attack surface. There are none.
There's nothing. Yeah.
Right. So, but there are key generators.
Mm-hmm.
But those key generators generate keys in a non-deterministic way. So what that means is that they spit out different stuff. You give it the same input, it spits out different stuff.
Truly randomized.
Yeah, well, it's got a source of entropy for the key generation.
Right. Yep.
Shannon min entropy, right?
Yeah.
For playing at home. But the process itself of that key generation is non-deterministic. And via the process that we have inside this infrastructure of cryptographic entanglement,
mm-hmm.
That's not quantum entanglement, but that's a pretty good analogy, right? But it's cryptographic and it's classical. The whole thing is classical computing, right? You can create an entanglement between these two key generators such that without having to send the key, that Alice can encrypt a vaulted object and Bob can generate the key to decrypt the vaulted object.
Uh-huh.
So that's the sense in which that's essentially the heart of the proof that I was talking about before.
Yeah, okay.
And I mean, there's proof and there's proof. There's also implementation and blah, 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 blah.
Sure, and scaling and all of that sort of stuff. Yeah. So it's a technology that doesn't rely on, the whole internet doesn't have to adopt it, like it might have adopted login by Google. Like it's not like that. A single person and a single application can use it and then it works.
Well, there's always a network effect equation.
Of course, that will improve things, but it doesn't require that.
No, that's right. It can really a vaulted object is a vault to self technology, right? So if you want to secure your own personal data,
right, you need
not even do it this way, and be a hermit.
What happens then if I become incapacitated, or like can someone else access that? Like, is there a method for an estate, for example, to?
Yeah. So what this thing is. It's like a gemstone with many facets. There's many ways to view it, and one of those is that it's a secure, self-sovereign digital identity protocol.
Mm-hmm.
So what you're talking about now is the protocol aspect of that identity framework. And so here's the thing: people upgrade their phones, right?
Mm.
They also do stupid things and lose them.
Right?
Yeah. And so if you lose your phone or you just need to upgrade it, what do? Because that secret is on the device. And it obviously can't come off. You can't just pull it out and put it on anything. So what you do when you first boot up your identity on this framework is you find some people that you trust to be able to identify you.
Okay.
Right? So now they might be your friends, but maybe your friends are flaky. Maybe you need to go and see your accountant and your lawyer, or somebody that you do really trust. So and what you have to say to them is, look, don't do it over a video conference. Right?
Do it in person.
That could be AI, right? Might be an AI construct. Right now,
for sure. Stranger things have happened.
Yeah, that's right.
Yeah.
And let's have a coffee. You have to eyeball me and be really certain that it's really me. And then I want you to press the button on the app that I got you to set up that maybe you understood, maybe you didn't. But I need you to press that button for me. And then that gives me a shard of that secret. It's not really a section, but it's a related chunk.
Yeah.
And if I get enough of them, if I get, 3 of the 7 or 10 of the 20 or whatever, then that can recreate that secret on my device.
All right.
Boop, pops into my TPM and I'm back.
Right. Gotcha. Okay. Yeah. So that's a good way to handle that.
And the other interesting part of that identity protocol is what we don't do is store your private identity attributes. Right? There's no point doing that. Now, I don't know if you've ever, booked into a hotel and they need to take a photocopy of your passport, or interacted with the Victorian state government where they need you to photocopy your driver's license and mail it into them. And this is all completely spurious nonsense in terms of identity security.
It's the worst. It's the worst. No, I won't say the name. A telco proved that brilliantly a couple of years ago.
Yeah. Well, everyone's proving it brilliantly all over the place at the moment. It's ridiculous. So instead, we get the user to API into Vic Roads, API into DFAT for the passport number, and go, do you know what you're talking about? Do you know your own passport number? Do you know your driver's license number and expiry date and all that stuff? Because those are the identity attributes. But what we don't do is record them. We could securely, and we don't, because we don't need to. We record, tick, verified, bang, bang, we've got a verified.
Yeah, that's all you need to do. There's a transaction that occurs where that verification happens, and if the result of that verification is yes, no other data needs to be stored except for the fact of the verification.
Yes, and we create a bulletproof, quantum secure, redundantly stored digital artifact of that proof. And that I suppose is a good segue into the discussion of digital seals. And what I'm talking about is ITS digital seals, Claude Shannon approved, most likely. And so I did mention that our cryptographer was part of the team that built the X509 spec. Right, so he has some history with this going back more than 3 decades. And this is his gift to the world in the sense, quantum secure digital signatures and digital seals. In our framework, they're really the same thing, and they're really digital seals. You can seal a contract. It's not very popular. Most people put a signature on it. It used to be that people were absolutely illiterate. And they couldn't even write their own name, let alone sign a document. And so medieval red wax seals. That's your identity. Your identity being affixed, an artifact of your identity being affixed to a promise, to a document.
Yep.
And we do the same thing, but in the digital world. And really, what a digital seal is, just for the nerds out there, is a JSON file, just the seal itself, that interacts with this whole identity piece that I'm talking about, and an ASCII text file, right? Because back in the medieval days, the preferred medium for writing a deed or a contract was lambskin parchment.
All right.
Not any old bit of parchment, but lambskin.
Okay.
Because lambskin has a layer of subcutaneous, under the skin, fat.
Yeah.
And the lining process of preparing the parchment would dissolve that layer, and then you could just write on the top of it, no problem.
Right.
But when it came to rubbing the ink off to remove the ink, it would delaminate.
Yeah.
Actually, do you know what? I've never thought of this, but the word delaminate is the word
that's
laminate.
where it comes from. Do you reckon?
Lamination? Yeah, probably is. I don't know.
I'll look it up after we're done.
You know, get an LOM to work it.
We'll say we're right, and then I'll look it up.
Yeah,
if we're wrong, I'll edit.
So that the lambskin parchment was write once technology. So you sealed what you could see, and you knew that nobody else has got in there and monkeyed with it. Well, after you've sealed it, nobody else can get in there and change it.
Change it, yeah. It's unalterable.
Yeah, correct. So absolutely perfect and appropriate technology for the time, except if you're a sheep.
Yeah.
And so what we do instead is we have a ASCII text file, limited set ASCII. We remove anything that looks like an invisible character that might mean anything. And so we have limited set ASCII because why? Because that you can't modify. It's not a PDF full of layers that are invisible. It's not a docx full of wingdings. It's just a simple ASCII text file.
Right.
And so you put that ASCII text file next to the other text file, which is the JWT of the seal, and you then hash the lot of it and encrypt the hash. That's how you stick these things together cryptographically. Then you've just stuck your identity.
So that would be useful for, let's say you had created a piece of digital artwork. That would be useful if you had created a contract or an article or anything that is in digital format. This was the dream of the NFTs 5 years ago, if only they'd known.
Correct. Absolutely. Now, thank you for that, because this is one of my favourite little hobby horses to rant on top of. The NFT industry, the blockchain NFT people, did a magnificent job, you have to hand it them, of convincing people that a NFT somehow contained some content.
Some exclusivity.
Yeah, well, it doesn't.
Yeah.
You can't put an image on a blockchain.
No, because you can make an exact and perfect copy of that thing.
Well, that's part of the physics of the digital world.
Yes.
What I'm kind of talking about is the physics of blockchains themselves.
Oh, okay.
So, in other words, you can, I think Bitcoin, the original block size was 1 meg.
Right.
Right?
Yeah.
You get a 2 meg image in a 1 meg block. That's not going to work.
Right.
Right. So blockchains were never designed.
Was not. Yeah.
For media. Right. Like some people have tried to, squeeze media into blockchains. A fool's errand, I think. But really, your content sitting on an ordinary web server at the end of the day. You might, put an IPFS layer on top of it or whatever. Right. But it's just sitting on a garden variety web server. And your blockchain record, your non-fungible token, has some JSON in there with a URL. It's a pointer to
that location. Yeah.
To that location. Now, a lot of things can happen here, right? You might forget to register the domain and the domain goes away. Right? The folder structure might change.
Right.
The file name might change.
Right. Anyone that's written websites knows all of this.
The actual content of, exactly. Yeah. There's been a broken image leak. That's what happens to your NFT in 404s. Right. And I used to enjoy Google searching for NFT 404 and reading the litany of horrors of people spending house deposit sorts of money on buying a picture of a monkey or something, and that all this just 404ing and
the server goes down and that's it. It's gone.
There's nothing secure about an NFT. There's really nothing secure about it. But if you can put the content inside of your token, JSON Web Token JWT, for example, what we call an object, a vaulted object, more expansively a vaulted data object, that's what we're talking about, data objects, in a way that you can possess and therefore legally own and you can keep people from looking at it, or you can expose it if you want,
Yeah.
then that's a whole different thing. And that's really why this infrastructure exists. And this is, I suppose, my contribution and my conversation with our cryptographer, because I was like, yeah, we have to solve this problem. This NFT thing is a great idea, horrifically badly implemented. Right? So, and then it becomes digital assets. Right?
In the truest form, like an actual asset.
Yeah. So we have vaulted objects on one side, and we have digital seals on the other side. Now, they're very similar. They're both JWTs, so basically look the same, except one has a content cipher inside it, can hold anything, and one doesn't. It can attach to a document, but that's, ASCII file, right? It takes not even kilobytes probably. So what a digital seal can do is it can create a deed, right? And that deeds are powerful legal instruments. They're more powerful than contracts.
Right, you have to because they're transferable, is that correct?
Well, it's instant transference, right? If you promise to transfer legal ownership of something, and then you seal that promise, it's done.
It's done, yeah.
You don't own it anymore, right? So a deed, another name for a deed at common law is a specialty.
Okay.
And it's special because you don't require consideration, right? If it's a contract, you do.
Yeah, okay.
Ask a first-year law student, they'll tell you. Consideration, it's an essential element of a contract. But a deed or a specialty, you can just go, whoop.
Right.
Instant transfer.
And it's done.
Of legal rights. Yeah.
Right.
So now that's not the only thing you can do with a deed. You can also attest to, let's say, the truth of a thing. Right. So you could put a seal or a deed, if you need to, onto a vaulted object that somebody else owns. So when you create a vaulted object, it's like you've put your seal on it because it's attached to your identity. It's obvious whose it is. And people need KYC onto our framework.
KYC?
Know your customer.
Okay.
So because we've seen, it's obvious that you need to do this, I think, but we've seen in the blockchain world what happens when you have a bunch of anonymous sock puppets from 4chan flooding the marketplace. And what do? They defraud each other. They scam, they rug pull, they misbehave. We don't want that.
Yeah.
What I want is to be able to interact with a digital world where even if I don't know exactly who I'm interacting with, I know for sure that someone knows who they are. And if anything goes wrong, like really wrong, I can sue them. And they know that I can sue them, and therefore they don't even go there, right? And this could be the longest possible answer to your original question around identity and the governed AI story.
Yeah.
Because what the foundation of this concept of governed AI, which is this infrastructure we've been talking about, is the ability to evidence the user's my duty of care, right? So you've probably used Midjourney, right? All those image generations, videos or whatever, right? But just let's talk about image generation for simplicity. Those images can be lovely. They can also be defamatory.
Of course.
Right? They can be bullying, sexist, racist, fraudulent, name your harm, right? And there are sure guardrails, but like jailbreaking.
Sure. Yeah.
So because those companies they're sort of playing a risky game in the sense because there's a thing in this world called vicarious liability.
Okay.
And they can be held responsible for the harms created by their users in certain circumstances.
If they've provided the tools and not taken sufficient action to prevent it.
Correct. That's right. So imagine now if every time you generated some content on behalf of a user, you're the platform operator now, right? Then you deliver that content to them as a vaulted object with their name on it.
Right. Right.
Right. Their identity attached to it.
Hmm.
And let's say it's some horrific defamatory thing against, I don't know, some big famous pop star, just for an example. Are you going to publish that?
No, of course not.
What are her legal team going to think of?
Yeah. Yeah.
No, forget. Like, let's just pretend this never happened. So you govern yourself.
Yeah.
In that situation, right? This is AI governance at the output level from a user's perspective, and there are various different facets of the gemstone there. Like you can look at that in terms of the inputs. You can look at that in terms of the LLM itself. Like the LLM itself, that essentially becomes a trade secret. If you're providing content, or if you're training the LLM, let's say, based on confidential information, based on trade secrets, the LLM itself becomes a trade secret. You don't want to do that to a public model, stuff. But even your private model, that then has to be protected, right? Because somebody exfiltrates that.
Absolutely. That's all you've got.
Harvest it now to decrypt it later.
That's all you have, yeah.
Yeah, that's right. It's open sesame. It's Aladdin's cave. Come, Q day, which obviously isn't a day. But
let me ask you one final question. And I'm sorry, I was going to ask you about the VR shoes, and I didn't.
Yeah.
So
another episode.
Maybe that's a topic for another day. Any of the listeners, Scott, at one point, many years ago, well, you mentioned the conference in 2014, invented shoes. I don't know if you got to a prototype stage. I don't think you did. That could be operated so that a person could virtually walk, but also physically walk. Have I got that right? I don't want to talk about it too much,
right.
But
Just in brief summary, it is a pair of shoes that's functionally equivalent to an omnidirectional treadmill.
Right. Yeah.
So it's a physical device. It's a pair of shoes. You wear it. What's good about shoes is that it's easily manufacturable, easily shippable,
portable.
Low power required. Blah blah blah. Right? So there's a whole bunch of cool advantages to it. And there are projects out there that have progressed more than I have in the implementation.
Yes.
But haven't quite gotten to where I got to in the conceptualization. So I think I've still got a few tricks up my sleeve. And so I filed a US patent on this. I went through IP Australia with a provisional patent. I went through the PCT application phase, 18 months of reserving priority dates, etc., and then to fully granted US patents, which was granted in the year 2000, right? And it's well since expired.
Right. Okay.
But I like that. It's a mark in the sand, right?
Yeah.
And I can't quote the patent number, but so that's a super fun project. That has actually animated my career as a technologist. Like a lot of the different things that I've done, the video analytics company that I built, for example, was an artifact of trying to solve dastardly problems with the sensing systems for the VR walker.
Right. Okay.
Yeah. So that's pretty good fun.
So thank you for that. My question is this, just related to that entirely. And that is, what validation have you got at this point that the technology is correct? I mean, theoretically, you know that the cryptography is sound. Have you validated the process, or is that too hard to do without quantum computing to actually test it, to harden it?
This is really perhaps the most interesting question about the whole thing.
Yeah.
Right. Is how do you do that?
Yeah.
When you can't test it against a quantum computer in 20 years' time.
A thing that is theoretical still.
Yeah, that's right.
Yeah.
So, and I mean, we can build apps, right, and push them out into the world, and people can get it, but that still doesn't prove anything.
No.
In terms of what it needs to.
They'll be secure, but do we know that is more secure than the next thing?
Yeah. Well, I mean, if you give somebody an app, they can't, what is that? They can't even get into it's not even them making API calls.
Right.
So when it all boils down, the only thing that we can actually do, and the only thing that actually makes any sense, is to step people through our theoretical proof, to get them to understand what we're doing and to show them how, in the same way that Claude Shannon proved the perfect secrecy, essentially, of the one-time pad, that we have extended that into the world of key management, made it work practically on the internet in an ITS way, an ITS secure way.
Mm-hmm. And as computing improves, then you can test more and more of this until there is a final quantum computer that can be used to test and to demonstrate.
Yeah, and if Shannon's right and our implementation is in accordance with Shannon's principles, then it remains true. And central assertion here is that the cipher reveals exactly nothing about the message.
Right. Yep.
And that's quite possible. Shannon proved it. That paper has stood for 77 years.
It's a mathematical proposition.
It's a logical...
not, yeah,
it's a logical, theoretical proof.
Yeah.
So unless there's something else that somebody's concerned about, i.e. some problem with the implementation, potentially, then that theoretical proof stands. Unless you can challenge it on the theory, then that stands. And not only is that the only thing that we can really do, but it's the only thing that really matters.
Yeah, right, absolutely. Scott, you're bringing the receipts to the internet. Thank you. We've discussed a lot today. Is there anything that you wanted to bring up at the end here? Is there anything else you wanted to say that I haven't let you explain yet or go into?
Yeah, really, because you and I both now are deeply into the idea of agentic coding. Only ones, of course. And I think it's a delicious question as to what's happening to software development.
Right.
Like what's happening with the software industry at the moment.
Right.
We've heard about the SaaS apocalypse. I'm really interested I've got some opinions on this, but I'd really like to hear your thoughts on this.
Look, I have this viewpoint. Whilst there are millions of people like us who are able to use Codex and Claude and other tools to write software and can do it. Like I have rewritten several tools that I used to be paying for and now have my own tool to do. Is this what most people will do? No, they won't. Someone gave an example recently and a completely different scale, but anybody can go to a shop and buy a bread maker and make their own bread at home. They don't do it. They go and they buy a pre-made loaf of bread because that's what they want. A pre-made loaf of bread, no fuss, no trouble. This is still going to be the future of software. Whilst to you and I and many of the people listening to this podcast, it is very, very easy to write a piece of software now that does exactly what you want it to do, and you can add features at will. Most people won't do that still. And that's the truth. And I've seen that. I've seen people go, oh, I can write a piece of software now, pick up Codex and do that, realize that there's a whole bunch of things they don't know and can't figure out, like how to secure it, how to deploy it, how to quality check it, how to do it's that last 10%, all of those things, and then they give up.
Yeah, absolutely. I think that's all true. I do have, I suppose, a different vision for one little part of that, which is that I think that software is getting softer with agentic coding, and it's also getting democratized.
Yes, that's true.
And the business model is changing.
Yeah,
and I think that what's happening here is that the applications themselves will absorb the abilities that you and I are just playing around with the very earliest incarnations of. So in other words, I think you'll be able to say to your phone, talk to your agent and say, I need to do this now. Right? Or it says to you, hey, I think you need to do this now.
Yeah.
I think this is your next best action. So we have a bunch of associates that I call the epistemology crew.
Okay.
People that are expert in their little niches of this whole epistemology game. So epistemology is the philosophy of knowing. Like how do you know something? How does your agent know something? How does your AI know something? And this is deeply, tied up with this idea of ontologies. And if you really, pulling the lever on that, it's dynamic ontologies. That's how it knows. Your way of knowing things. Well, ours has just changed over the last hour and a bit, whatever. And so I think that software applications are going to have the ability to morph and to change in real time according to what they know about you.
Right, without the user having to proactively do that. Like it will be the proactive.
I can't imagine my mum using Hermes agent.
Yes,
to,
right.
Agentically code some, software.
Right, but the result of that being, and your mum is a good example, not that I know your mum, but somebody who doesn't know what they want, but will gladly engage when something better comes along. Is presented to them.
Absolutely. And to be fair to my mother, sometimes she does know what she wants, right?
Of course.
And so she can express her wants and needs, and could probably find a button on her phone if it was, right there in front of her to press it and say, this is what I want.
Yeah.
And that's pretty much what we're doing, right? So I think this is all deeply interesting. I think this is the way that software gets softer. And I can see this, the march of history in IT. I mean, computers used to be hard, like hardware as well, and punch cards and all that sort of stuff. And through operating systems and the Windows interface, Windows and the generic, and all this stuff, it's becoming softer and more human.
Right.
This is what I love about the AI
human.
thing. It's becoming more human technology. And so I just have to give a shout out to my buddy Peter Cranstone in Florida, because he has a really interesting technology. He's a web technologist, and he's created a thing called augmented HTML, which is also a soft technology because it can restructure a web application in real time, like the whole menu structure of it and everything, according to your needs, to your private information. And you have to have a way of keeping private information, and that's been the basis of our conversation over the last 3.5 years.
But this is the future, like presenting to the user proactively, here is something that you might find useful.
Yeah, absolutely. And his latest thing is what he calls the autonomous execution constraint, or AEC. I call it Cranstone's boundary. So this is where an agentic system, an AI agent, can't execute on an action that is irreversible, right? It can't write a script to a pharmacy to give you some medicine, because if you take that medicine, you can't untake it, right? It's an irreversible action.
Yeah. That's worse than an email that shouldn't have been sent.
Yeah, exactly. And, a payment is generally irreversible as well. It's a whole lot of things. But it can't proceed with that unless it has the evidence of authority to act, in this case from a pharmacist or a doctor. And once it has that authority and does the action, that it creates a secure digital artifact, a certificate essentially, that everything was tickety-boo, that was all in place. And now the people downstream in that industry can just look at that and go, it's fine, we can do this. We can rely on it.
Yeah.
So it's that reliance piece becomes really important. I suppose that's, part of the governed AI, framework.
Yeah, it is. That's exactly what it's part of. It's a chain of authority, right?
Yeah. And so where this sort of ends up is the question of, well, what's left for the humans, right? If AI, if we're to believe what we're being told at the moment, AI can, unpack this, utopian vision, but we'll all be, horribly unemployed. Like, how do you square the circle around this? And what I think is really interesting is the question of, well, is this agentic AI thing that we're currently experiencing going to cause any problems? right? Because if it causes problems that the AIs themselves can't solve, then there are jobs for humans.
Totally. Absolutely.
And if it doesn't, well, we're in a utopia. So either you're going to still have a job or it's going to be a utopia.
Yeah. Yeah.
And, it's probably the former. So I don't think everyone's jobs are going away.
No, I think
soon.
history has taught us that utopias are unobtainable.
Yeah, well, I mean, it does depend on having a situation going on that's not throwing off negative externalities.
Yeah.
Right?
Yeah.
It's not causing more problem or causing problems as it
every
creates.
science fiction story ever.
Yeah, absolutely.
Is that.
Yeah, probably the Bible and the Quran and everything else. Bhagavad Gita.
Yeah, that's right.
Yeah.
Yeah. Scott, thank you very much for joining me today. As always, we could continue talking for a couple more hours. We won't. Maybe we'll do this again sometime. Thank you for joining me today.
Thanks so much, Errol. It's been an absolute delight.